Hello, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinars. And again, I'd like to thank Dr. Curtis Larson and also the NASA Engineering and Safety Center for sponsoring this series of webinars. So today we're going to be covering integration and differentiation of time histories. Now, typically when we measure vibration, the most common sensor is an accelerometer. So this is a very easy way in most cases to measure vibration. And it's easier to measure acceleration than it is to measure velocity or displacement in most cases. And there's various types of accelerometers. The one on the bottom left is a piezoelectric type, but there are also piezoresistive types, variable capacitance types, as well as several other types. And in the bottom right-hand corner, that is an example of a variable capacitance accelerometer. So we measure acceleration, but sometimes we want to know what the corresponding velocity and displacement are. And here's just an example. There's been a series of authors and researchers, for example, Hunt, Gaberson, and Bateman, who have published papers showing that dynamic stress is directly proportional to modal velocity. And we'll cover that in a future webinar. And these engineers have come up with a kind of a rule of thumb stating that a peak velocity of 50 inches per second is sometimes considered as the shock severity threshold for military components. So if a military component will be subjected to a shock that has a pseudo velocity of less than 50 inches per second, then shock testing may not be required or may be optional. But if that same component is to be subjected to a shock with a pseudo velocity of 50 inches per second or higher, then shock testing would be required. We'll cover more about that later on when we get into our shock units. And then there's some other different examples. For example, in terms of buildings or semiconductor fab facilities or historical buildings, there are different criteria in terms of allowable vibration, either in terms of velocity or displacement. So a typical specification that you might come across would say that the allowable building floor vibration limit is somewhere less than 2 inches per second. Then there was another engineer named Colin Gordon who established a series of generic vibration criteria for building floor vibrations in terms of velocity. And this is an ISO type spec, and hopefully we'll cover that in a future webinar as well. So if you were out in measuring the floor vibration in a building or a historic site or a factory, then most typically you would use an accelerometer, but then that data would need to be integrated to get the corresponding velocity so that the resulting velocity could then be compared against some standard or specification in terms of judging severity. Well, there are several ways of directly measuring velocity. One way is using a Doppler laser. Another way is using a geophone. Well, the laser is a very elegant way to measure vibration velocity, but it's expensive and it requires a direct line of sight. So if we have an avionics component with several circuit boards, then hopefully we could take the lid off the box, but then we can only point the laser at the topmost circuit board, for example. Let's see what else. So the geophone, this is used in oil exploration and seismology, and it's rather bulky. And here's a geophone. The diagram shows that there's a magnet at the core, then there's an outer coil and a leaf spring, and then you can see the cylindrical housing there. So the idea is that this might be, for example, mounted in the ground or on a floor, and there would be relative motion between the coil and the magnet. And I think the idea there is that the magnet itself would be vibrating vertically, and the coil itself is mounted on very compliant springs, so that would tend to remain stationary, and then the relative motion between the coil and the magnet would cause a current or voltage that is proportional to velocity. So that's one way for directly measuring velocity. Lasers, they're fun to use. They can give great data. So here's a laser, and it's, in this case, it's being used to compare the vibration of two similar guitars. And one of the big advantages of a laser is that it has no mass loading effect from the laser on the object. So I think we can neglect the effect of the photons. So let's see, the photons do not have mass, but they do have momentum. That's something that physicists understand, but maybe as engineers we have a tough time understanding that. But let's say that the photon momentum is negligible in terms of influencing the object. Whereas if we took an accelerometer and mounted it to that guitar via wax or glue or whatever, then that would have a mass loading effect on the object. Well, there are some disadvantages to using a laser. Of course, it requires line of sight. And actually, we have to realize that what the laser is measuring is the relative velocity between, in this case, the guitar and the laser source itself. So it's very important to keep that the laser source itself as still as possible. And there's different types of laser vibrometers. For this guitar image here, it's just a single point laser vibrometer. But there's other types as well. There can be a scanning laser vibrometer. In this case, we have a turbine blade, and using the resulting velocity signals over a 2D space and passing that data through some software. This really neat grid display with different colors is produced. So there's different types of scanning laser vibrometers and different types of laser holography, and it's all fun stuff, but sometimes more expensive than our budgets will allow. Now we can also measure displacement directly, and one way of doing that is through what's called a linear variable displacement transducer, LVDT. So here we have kind of a bridge structure here, and these LVDTs are being set up and mounted via tripods on the underside of the bridge. And the idea here is to measure the traffic-induced vibration on the underside of the bridge. Well, LVDTs certainly have their place, and they can be useful. Of course, displacement primarily happens at lower frequencies, so for the low frequency vibration that this bridge is going to undergo, the LVDT is a good way to measure that. But if we have like a small electronic box, avionics component with a circuit board, then that most likely would be subjected to higher frequency vibration with a corresponding higher frequency response, and the LVDT would just be impractical for that case. But they're great for example, for civil engineering structures. Okay, now there's different ways we can measure velocity and displacement, as I've mentioned in previous slides. Well, here's another way, and I'm going to call this the old school analog method for measuring velocity and displacement via an accelerometer. So we're going to have an accelerometer, that's the transducer, and it's going to be a charge mode piezoelectric type. And there was a device at one time, maybe it's still commercially available, called a Brüel & Kjær 2635 signal conditioner or charge amplifier. And this has all sorts of knobs and buttons on it for dialing in the sensitivity of the sensor. And on the bottom left-hand corner, there's a knob. And using this knob, the output can be set to either acceleration or velocity or displacement. So what this charge amplifier / signal conditioner is going to do, or will do, is depending on that knob setting, it will either do an analog integration to velocity or an analog double integration to get displacement. So the resulting output signal would have volts proportional to either acceleration, velocity, or displacement, depending on the setting of the various knobs there. But one thing that's interesting is that in order to do these outputs, the user has to select a high-pass filter. And that's particularly critical for velocity and displacement. And that's needed, for example, to filter out any spurious baseline shifts or spurious drifts. And when we get further into integration, you'll see that it is necessary to do different types of either high-pass filtering or trend removals. And one of several reasons that is required is because when we're measuring acceleration, for example, and trying to integrate to velocity, we do not know what the initial velocity is. We just don't know that. So there's some precautions and things we need to do. Just to close out this slide here, the minimum high-pass filtering frequencies are 0.2 Hertz for acceleration and 1 Hertz for both velocity and displacement. Excuse me. Okay, here's some typical building vibration limits. So for example, if you had a charge mode piezoelectric accelerometer, you could mount it on the floor of a historic building, and then you could take that signal through the Brüel & Kjær 2635 charge amplifier and get the velocity output. Or if you just have an acceleration time history measured via a different measurement system, there's different post-processing digital integration that you could do as well. We'll be covering that here shortly. Here are just some typical standards. So if you start to do a Google search and go through different references, you might see something similar to this. This is from some organization called the Transportation Research Board, Building Maximum Structural Vibration Criteria. And the criteria is in terms of the limiting peak particle velocity. So for historic buildings, the velocity threshold upper limit would be 0.5 inches per second. Now, the concern here, for example, is let's say there's a building, and outside that building there's a busy roadway, and large trucks are coming up and down that roadway. Well, that generates groundboard vibration that can affect that building. There's also another concern is what if there is a construction or demolition of a nearby building? Well, in that case, there's going to be a lot of vibration due to the construction, and that vibration will also be transmitted via the ground into the foundation of that historic building. So there are different concerns there. For residential structures, also 0.5 inches per second. For newer structures, 1 inches per second. Industrial buildings, 2 inches per second, and bridges, 2 inches per second. And of course, if you, like I mentioned, you can come across other tables that may have slightly different values, but this is typical enough. Okay, here's something interesting. I used to live in Arizona, and this is one of the most notable distinct buildings in the downtown Phoenix area. So it's the Hyatt Regency Hotel, and on top of that hotel there is a revolving restaurant, and if you start at the ground floor and take the elevator and go all the way to the top without any interruptions, that is a very fast elevator ride. Well, it turns out that the people that the hypothetical, or maybe there is a elevator engineering society or trade group, whatever they might call themselves, have come up with limits, recommended limits, and these limits are in terms of the comfort of the elevator passengers. So here we have some metric units here. For acceleration or deacceleration, the limit, I guess if we want to be conservative, should be less than 1 meters per second squared. Now, if we take the gravitational acceleration and we just for simplicity round up, 1g is equal to about 10 meters per second squared. So the limit is effectively less than 0.1 g's for acceleration and deceleration. The speed is less than 7 meters per second. That's the limit, recommended limit. And that's probably not as important because our bodies do not sense speed. We could be in an airplane cruising at 30,000 feet going 500 miles per hour, and we could get up and walk around the cabin and our bodies would not detect that we were traveling at 500 miles per hour relative to a fixed point on the Earth. Well, it's not speed that's critical, it's rather the acceleration and deceleration that either ramp up or ramp down from that speed. So in that sense, I guess speed is important in that it affects acceleration. There's also something called jerk. Now, jerk is the time derivative of acceleration. And we don't usually deal with jerk, but that parameter does exist. And the jerk rate is less than 2.5 meters per second cubed. So our bodies do detect jerk. Our bodies do not like to be jerked around. And of course our bodies also can detect acceleration because force equals mass times acceleration. There's also a requirement for the sound level and the ear pressure change shown there. So all of those are important for the passengers on the elevator. So what I actually did is I had a laptop computer, and this was about 10 years ago, with a little kind of a student variety data acquisition system, an accelerometer, and I went and actually measured the elevator vibration for a straight non-stop ride from the ground floor up to that revolving restaurant. So on the top here you can see the acceleration, and I've made a note that I've done a 2 Hz low-pass filter on this data to filter out some kind of high-frequency noise. So this is the elevator upward trajectory, and the y-axis for the top graph is meters per second squared. The x-axis is time in seconds, and you can see at the onset here the acceleration gets up to about 1 meters per second squared, and then the acceleration persists for about 4 seconds. And then during the constant velocity part of the ride, there is a little ripple effect going on, probably some resonance between the elevator and its different cables and springs and so on. And then for the deacceleration here, you can see it's not quite, but almost kind of a reflection, inverted reflection of the acceleration. And that's what it takes to de-accelerate that or decelerate that elevator to arrive at the top floor. So on the bottom graph here, this is integrated velocity. This was post-processing digital integration. Again, 2 Hz low-pass filter data. So we have the velocity in meters per second and time in seconds. So you can see we have the ramp due to the acceleration. Then there's a steady state velocity. And then we have the deacceleration, and the velocity is decreasing, ramping down. So here we have a jerk due to the onset of the acceleration. Then the acceleration is fairly constant, so the jerk is fairly smooth. But then as the acceleration is ramping downward, we get this jerk spike right there. Then we have this little ripple as the elevator is continuing upwards at a fairly constant velocity. Then we have this downward ramp here. We get another jerk spike, and then this ramp here, this upward sloping ramp, we get another jerk spike. I will mention that when I did this differentiation and processed this data, this low-pass filtering was a very critical parameter because depending on how I chose that low-pass filtering made a big difference as to what this final level was. If we take a look at these parameters, peak jerk, peak acceleration, peak velocity, peak acceleration again, for this Hyatt Regent hotel, that those parameters all fall within those recommended limits. Now, this data I took maybe 10 years ago, so since then maybe they've changed the elevator. Who knows? But if you ever get a chance to visit the Phoenix area, you can go and take that ride for yourself and report back to me. Okay, let's talk about some formulas here. We're only going to do this kind of just sort of an overview. For integration, typically what we do is we just use a trapezoidal rule. That works good enough. And this integration is a running sum integration. So let's let our acceleration values be these a lowercase a. So we have a sub 1, a sub 2, a sub 3. These are all the acceleration amplitude points up to a sub n. And there's going to be a delta t. Well, delta t is going to be the time step. So let's calculate the velocity using the trapezoidal rule as follows. So here's going to be the velocity at the first time point. Delta t over 2 times that acceleration. Now to get well, here's a problem already. We're going to say that's what our velocity is at point 1, but really we're missing an important piece of the puzzle. We do not know what the initial velocity is. More about that later on. Now to get the second velocity point, it's equal to the first velocity plus delta t times the second acceleration. So you can see here, this is a running sum. So the velocity at any point in time depends on the previous velocity, as well as this acceleration term here. And then for the third velocity, that's equal to the second velocity plus delta t, the time step, times the third acceleration point, and then so on and so forth. Then once we got to the final velocity point, we would again use this type of point where we would take the delta t and divide by 2. And it would be that last acceleration plus the running sum total velocity. For differentiation, it's a little more complicated rule, and the typical way you think of doing differentiation is just take 2 amplitude points and take the difference in amplitude divided by the difference in time. And that's a typical way for doing a linear slope. When we teach graphing and lines in algebra to students, we say, oh, for a straight line, y is equal to mx plus b. Well, that m factor here for oscillating vibration, we really need more of a robust rule. So this is a numerical integration handbook type rule here. It's a little more complicated, and I decided to show this as a MATLAB function. So what we do is we take our time step and we multiply by 12. And then in this case, for example, let's assume that y is our input. Let's just call it the input acceleration. And well, let me back up. Let's call y the input displacement. Let's say we have a displacement measurement, y, and we want to differentiate to get velocity. So for the first velocity term here, we have a formula. You can see it depends on 3 different displacements plus coefficients divided by 2 times delta t. And then for the second velocity point, then for the intermediate velocities, we have a more complicated formula here. And then for the next to last velocity and for the last velocity. So this is how to do a differentiation using kind of a higher order numerical approximation. And this tends to work fairly well for vibration signals. I guess there is a caveat though. When you're going to differentiate a time history, it's really a good idea to have plenty of significant digits. because if you're rounding off your time column, you could have 2 points that have the same time step given that you've rounded off, and that could really mess up the delta t factor and cause a spurious error. So if you're going to differentiate a signal, make sure that you understand the proper delta t for that data. Let's just take an example. So what do we have here? We've got an amplitude versus time. This is a sine function, and 10-second duration, frequency 1 hertz, sample rate 40 hertz. And let's assume that this was acceleration g. So let's go ahead and generate this, and this is going to be a review exercise. So we're going to go to our MATLAB GUI package here. So let's go to our GUI package, call this up, and I'm going to type in vibration data. Pause for a moment. MATLAB's a little slow this morning. Okay, we're up to version 5.5 in this GUI package. And by the time you actually download the software, we'll probably be up to a higher version. Let's generate a signal. This is a review exercise so far. Amplitude 1, duration 10 seconds, frequency was 1 hertz. Okay, we're going to do sample rate of 40. Let's calculate that sine function. So here it is. It's the same one that's on the PowerPoint slide. And let's just save this as sine underscore acceleration. So I'm going to save it to the MATLAB workspace. Okay, now that's in the MATLAB workspace. So I think next we're going to do a integration. We're going to integrate to velocity. Now, here's a problem. We know what the acceleration is, but we do not know what the initial velocity is. And that's actually going to cause us a bit of a problem. Well, let's go ahead and do our integration. So I'm going to just return, click the return button here. Now this is going to be new for today. Let's go over to integrate for select analysis on this time history. So this script integrates a time history. The input array must have 2 columns, time in seconds and amplitude. So we have preloaded into MATLAB, we have sine underscore accel. And let's see, our input is going to be acceleration g. Our response is going to be velocity in inches per second. Now, since we're going from g's to inches per second, one of the things we need to do is multiply by a scale factor of 386. So if we want to get, well, 1g is equal to 386 inches per second squared. So we have to account for that factor. And there's some options here. We can do trend removal either before integration or after integration with a couple different options. To start off, we're not going to do either. But let's just calculate and see what we get if we just do a straight integration. Okay, so what's going on here is this plot you've seen before. It's just our acceleration time history. 1g, 1 hertz, 10 seconds. And when we do velocity in this integration assumed that our initial velocity was 0. Well, to make all the integration work out with an initial velocity of 0, that results in an offset, a baseline shift. So the baseline shift here, well, if we take the mean value of this signal, it looks like it's going to be about 61 inches per second. So we have this baseline shift. Well, is that reality or is it not reality? Well, it's kind of up to us as we're just synthesizing this signal, but the same thing would happen with measured data. If we just took measured data with it where the acceleration began at 0, we would have something similar occurring in terms of a baseline shift. And so let's take this integrated signal, and we're going to call it sine underscore VEL. That's for velocity. Save it to MATLAB workspace. Okay. So we've just done that, and for the next step, we're going to take our velocity and integrate to displacement. So things are going to be pretty similar in terms, we do have to do, well, we have to do a couple of changes here. Our input now is our velocity time history. Our response is going to be displacement in inches. We've already done the 386 scale factor, so I'm going to say no. Don't need to do that anymore. For the prior to and after trend removals, both are no or none. And let's calculate and see what displacement we get. Well, on the left figure here, we have our velocity time history. Again, it starts at 0 and has a mean value of about 61 inches per second. So it has the baseline shift or offset. Well, the offset in the velocity turns into a ramp. We call this the ski slope effect. We get a ski slope effect in our displacement because we're assuming now that our initial displacement is 0. Well, to make all the physics and mathematics work out, that means we have an ever-increasing displacement time history. And so, is that reality or is it not reality? Well, this is a made-up example, but again, if you had accelerometer data that started at 0 and it was measured data, and you went through this whole similar process, similar effects would occur in terms of baseline shift in the velocity and a ski slope ramp in the double integration to displacement. Now in reality, once we get into the measured accelerometer data world, things can actually be a little more complicated because sometimes that accelerometer data can have a little bit of a spurious low frequency trend, or the data can just drift around a little bit due to different measurement imperfections. So whatever drift is going on with that accelerometer data, that will affect both the velocity and displacement. Okay, so let's see what we're going to do next here. So if we go back to the slides, the hard copy slides, well, it's a hard copy if you print it out, but the PowerPoint slides show just what we covered. We have a baseline shift in velocity, 61 inches per second. We have a ski slope effect when we double integrate to displacement. So the next thing we're going to do is we are going to repeat the whole process, but we're going to, in this case, do some trend removals. So let's go back to our acceleration signal. So I'm doing the copy and paste method here. Oops, wrong place. We're going to input our acceleration time history. We're going to take our velocity will be our output, and acceleration will be our input, acceleration g. The scale factor, 386, will be applied. Prior to integration, we'll have none for trend removal, but afterwards we're going to do a mean removal. So let's calculate this. On the left, you see the acceleration. You've seen this before. Starts at 0 g's at 0 seconds, and the 10 hertz oscillation, excuse me, it's a 1 hertz oscillation with a duration of 10 seconds. Integrate to velocity inches per second. Well, two characteristics. One, we've done this mean removal in post-processing, so our mean value now is 0. But in order to get a mean value of 0, we have to assume that our initial velocity was about minus 61 inches per second. So that's the trade-off there. Okay. Now, what if we want to save this? Let's go ahead and save this. And we're going to do our next level integration to get the displacement. So I'll put in sine velocity as our input. We have to switch around some labels here for our y-axis. So I'm going to have displacement in inches. Scale factor, no scale factor. And let's see what we're going to do this time. I think we're going to do the same thing in terms of, just want to double check myself here. Okay. So prior to integration, we're not going to do any trend removal on the velocity. It's already had a velocity. We've already done a trend removal on the velocity when we integrated for its post-processing steps, so we don't need to do that again. And for our trend removal after integration, so for our displacement, in other words, we're going to remove the mean from our resulting displacement. So let's go ahead and calculate this. Okay, here's our integrated time history. You could think of this as being the integration from velocity or the double integration from acceleration. So our displacement is occurring at, if we zoomed in, we'd see it's actually starting, I should say, at 0 inches at time 0. And then we can see we have a fairly well-behaved displacement oscillating fairly symmetrically about the 0 baseline. Well, if you look real carefully, though, you can see we get a little bit of drift here. And that just occurs because the imperfections of the integration process, different little imperfection things that occur. We're using trapezoidal rule. Maybe if we use Simpson's rule, for example, the resulting signal would have been better well behaved. I'll leave that to you as a homework exercise. And the trend removal process, there's some just built-in imperfections to this process. So even for this 10 hertz signal, we're seeing a little bit of drift in the displacement. There are ways to use higher order trend removals, and you can do that as a homework exercise if you like, but for this particular sine function, the higher order trend removals did not help the resulting displacement very much, but there are cases where higher order trend removals would be appropriate, especially if that acceleration signal has any sort of drift to it. Okay, back to PowerPoint slides. So I have the same thing we've just done on PowerPoint slide format. You can take a look at that, review that on your own. And of course, I want you to do this as homework exercises, so I put the steps there at the bottom of each plot. Okay. Okay, so now what we're going to do is one more step. We're going to do differentiation. So what we've just done is we've calculated our displacement time history. We've already done that. I'll show it to you again. Here's displacement. Let's save that as sine DISP for displacement. And we're going to learn a new trick here. Let's go back to our GUI, our main GUI page. Let's differentiate that displacement. So this is the first time we've run this script, vibration_differentiate. This script differentiates the time history. The input array must have two columns, time in seconds and amplitude. So we have preloaded into MATLAB our sine displacement, and our input was displacement, if I can spell correctly, in inches. Our output is going to be velocity in inches per second. Scale factor, no. And let's go ahead and differentiate the displacement and see if we can get back to velocity. Click on the button. So on the left here, we have our displacement inches per second. You've seen this plot before. It's a pretty good displacement plot, but you can see a little bit of drift going on. Now, as we differentiate and go back to velocity, you can see we get a very nice velocity time history. It's oscillating between -61 and +61 inches per second. Mean value is equal to 0. And it looks like those peak values there are constant. So we get a good differentiated time history. So let me just sort of summarize what we did is we took our acceleration that we synthesized, we integrated to velocity, did a first order trend removal, integrated one more time to displacement, did a first order trend removal. Actually, I said first order trend removal, I meant mean removal. Let me correct myself. In each case, we're doing mean removals. Then when we got to our double integrated displacement with its mean removed, then we differentiated back to velocity, and we get the velocity that we are, in fact, expecting. Let's just kind of do one other little review exercise while we're at it here. Let's go down to under miscellaneous, single degree of freedom response, sine random and Miles equation. This is going to be an intermediate menu. So we're going to take the top option here, which is steady state. Well, okay, sorry, told you the wrong thing. Let me back up. Okay, what I meant to do is go to amplitude conversion utilities. So let's go to amplitude conversion utilities, and let's do steady state sine amplitude. And we're going to input an acceleration. So for our exercise here, we had a 1g acceleration. That's what we synthesized the sine function to be a 1g 10 hertz sine function. So if we calculate, what do we expect? Well, for the velocity here, let's see. Our velocity here is, okay, I made a mistake. I make mistakes, and I don't mind making mistakes because sometimes you might make the same mistakes that I do. This was a 1G 1 hertz signal. Okay, it's Saturday morning in Huntsville. It's 8:22 a.m. and I think I need to wake up a little more. Okay, so our frequency for our sine function, our original one we synthesized, was 1 hertz. So that will give us a velocity 0 to peak of 61.43 inches per second, which we see here. And these are using the formulas that we already covered when we did the sine vibration unit. And what do we expect for displacement? 0 to peak, almost 20 inches. Excuse me, peak to peak would be 20 inches. 0 to peak would be about 10 inches. So you can see 0 to peak here, we get about 10 inches for our displacement. So our integration results are matching up with what we expect using the formulas that we covered way back when we did the sine vibration unit. So that's all well and good. Okay, so in fact we just did this little review exercise here, and the results we looked at are on the slide. And here I've correctly shown it's 1G and 1 hertz. Let's take a look at some pyrotechnic shock data. So we're going to be covering shock in earnest in some upcoming webinars. But here's acceleration G versus time in seconds, a pyrotechnic shock event. This is measured data. So what are we going to do with this? I think we're going to be doing some integration with this. So that's acceleration time history. And let's go ahead and do a integration and to velocity. And we're going to start off by not doing any trend removals. So let's go back to vibration data. Integration, we're going to integrate a time history. And we have, this will be an external ASCII file, pyro_test.txt. Our input will be acceleration in G. And our velocity in inches per second will be our output. We do have to apply the 386 scale factor. No trend removals. So on the left we have our input time history. That's from the measured data. On the right we have our integrated time history for velocity. And in this case, the velocity starts off pretty close to 0. In fact, the first point should be exactly 0. We have, excuse me, the shock event here, and then there's some drift occurring. It looks like there's a spurious drift that occurred after the initial pulse there. So if we want to get an estimate of what the true velocity is, we probably need to do some trend removals. So let's see what our slides tell us to do. Okay, let's do a 30 Hertz high-pass filter. So we're going to repeat this integration here, but for our trend removal prior to integration, we're going to do a 30 Hertz high-pass filter. Now, for pyrotechnic shock, it's common to represent the derived output test specification. Let's say we're deriving a test specification. We would derive that beginning at a frequency of 100 Hertz, and then probably go up to 10,000 Hertz. That's typical. So in many cases, we kind of throw up our hands and say, it's the high amplitude, high frequency energy that's important, and we cannot simultaneously accurately measure high amplitude, high frequency energy while still trying to measure low amplitude, low frequency energy. It's just tough to do in a pyrotechnic shock environment. So it's considered permissible to do some low frequency trend removals or high pass filtering. So let's go ahead and high pass filter and do this integration from acceleration to velocity. And on the left here, you can see our acceleration time history from our measured data. On the right, we have our integrated time history to velocity, so velocity in inches per second. And in this case, the resulting velocity is oscillating in a rather stable manner about the 0 baseline. So is this reality? Well, I would say this is plausibility. This is plausibly what the velocity is. And as to what the correct high-pass filter or trend removal should be, it's really a matter of engineering judgment. And the approach I would take is say, okay, whatever you do, just document whatever you did. So if you high-pass filtered, state that you did so and state the frequency, or if you did whatever trend removals. One thing we also need to check when we have this high amplitude, high frequency shock data, we probably have a high sample rate. And if we're doing anything with low pass filtering, it's a good idea to double check the filter stability. And this has to do in part with the precision of the numbers with significant digits and so on. And in this case, for the 3 filtering stages shown here, we have good stability. But if we try to filter down at maybe 1 Hertz high pass filter, we'd probably either have marginal stability or maybe even instability. So just make a mental note to yourself that usually we kind of just ignore or gloss over stability, but it's a good practice to double check what the filter stability was. And one way to determine whether or not you have a stable filter is just to look at the output data. If you get some really crazy peak or spike or offset or trend, then it was probably an unstable filter. In fact, let's just do a case. This is just kind of off the cuff here. What if we tried to high pass filter at 1 Hertz? What would happen? Well, we still get something that is perhaps plausible, but we're marginally unstable. Well, it looks like MATLAB retains enough precision and significant digits that we still have a stable filter at 1 Hertz. So is this reality, or, well, this is plausibility. It certainly looks different than our 30 Hertz high pass filtered. So again, it's a matter of engineering judgment. And I'm just going to play around. What if I just made a 1/10 of a Hertz high pass filter? What I'm doing now is I am playing. I am just playing around. Okay, well, we're still at marginally unstable. but we do have a stable signal. Again, what is reality? And also notice it's just a characteristic of doing this filtering process here that we have a little thing going on at the initial onset of the signal, and just due to the filtering process itself, we get that a little initial ramp that hopefully we can say is negligible, but it is an artifact of the filtering process as well as the integration process. Okay. And integration itself is a form, well, if we low-pass filter, for example, and if we integrate, integration is somewhat analogous to low-pass filtering. And differentiation is somewhat analogous to high-pass filtering. Okay, let's see what we have next. I think we're kind of in a home stretch here, but one other topic. So hopefully you'll have some test data that you can use as an example to practice with these MATLAB scripts. Now, do you remember we did PSD synthesis? This was in a previous unit, and we did a time domain. Well, the idea was to get a time domain, a time history signal, given a power spectral density specification. So we had a way of doing that using the software program that I wrote. And what we actually did there is, in fact, let me just kind of redo this here, or repeat a previous example. Let's go to vibration data. We're going to do an input of a PSD, power spectral density. We're going to do a time history synthesis, beginning with white noise. And let's call up one of our favorite specifications. It's our navmat underscore spec.psd. English units, I'll just say 20 seconds. Choice 8, let's see, is that a good choice to make for delta F? Choice 7, 8, just pick one. We're only doing 20 seconds, so it's going to go pretty quick. So we have our PSD on the left. Okay, that's the navmat specification. You can see this PSD, we have the red line is the navmat specification. And then we have two tolerance bands, plus and minus 1.5 dB. And then the result of our synthesis, if we look at our time history, acceleration time history that we synthesized, and calculate what the PSD is, you can see that it falls within the tolerance bands. If we had taken a longer duration, that would have been a smoother synthesis for the PSD of the synthesis. We get an oh, where did all the figures go? Okay, Windows does that sometimes. It's a bit of annoying. Okay, here's our resulting acceleration time history, acceleration in G, versus time in seconds, 20-second duration. And this is the time history that corresponds to that PSD. And I also want you to take a look. We also get a velocity time history for our synthesis. So we have velocity inches per second versus time in seconds. And I want you to note that both the acceleration time history and the corresponding velocity each oscillate symmetrically about their zero baselines, the respective zero baselines. Then the other figure here is our displacement time history, inches, displacement inches versus time in seconds. It also has a mean value of 0. So we have a matched set here of signals, acceleration, velocity, and displacement. And we could take these, for example, and we could use these waveforms to perform a shaker table test to that navmat PSD specification. Or we could take the resulting ASCII text files and apply these to a modal transient finite element model, for example, or a spring mass model, whatever we might have. So we could use these for analysis purposes as well. So that's just sort of a review of a previous exercise, but I want to give you some more insights to that process beyond what we covered before. So the process was that we start off by generating a white noise time history. Then we manipulate that time history via fast Fourier transforms and inverse fast Fourier transforms so that it satisfies the PSD specification. Well, that's all well and good, and perhaps most people doing this would just stop at step 2, but if we just took that acceleration time history from step 2 and we integrated to velocity, we'd have an offset, a baseline shift. Or if we double integrated to displacement, we'd have a ski slope effect. And that's not very good because we want each of those 3 signals to oscillate about the 0 baseline. And it's actually a tad more complicated than what I just told you because probably for velocity, instead of getting just a clean baseline shift, there might be a little drift there. More about that later. So what I would do is I say, after step 2, I'm going to take that acceleration signal and I'm going to integrate that to velocity. Then I'm going to take that velocity signal in step 4, integrate it to displacement. Now by the time I get the displacement time history down at step 5, there's going to be some offsets and ski slopes and trend effects, and so just sort of as a rule of thumb, I found that a good way to correct that is to do a 3rd order polynomial trend removal from that displacement. That works out pretty good. And also I do a few other couple steps to clean it up. I apply a tapering using a half cosine function to the beginning and end of the displacement. And just for a fraction of a second, just to clean it up a bit. And there's some reasons for doing that. Particularly because we're going to have to go through the differentiation steps. It just sort of helps clean up the differentiation. So for number 7, I then take that displacement from which the 3rd order trend has been removed, and also with the tapering. And when I say tapering, if any of you have played around with acoustics or sound processing, in the acoustic world that would be called the fade in and fade out. But anyways, I take that displacement function that's been cleaned up from step 6, I differentiate to get velocity, then I differentiate again to get acceleration. So that's how I come up in step 7 with a corresponding set of displacement, velocity, and acceleration, where each one of those 3 signals oscillates about the 0 baseline. And that works out pretty good. So that's all for today, and I hope you've enjoyed this webinar, and look forward to catching up with you on future webinars. So thank you, and goodbye for now.